Greetings and salutations, everybody. This is Jacob. So, where do we even start with this problem? It seems complicated, doesn't it? Well, let's first turn our attention to this diagram here. This is the tightest point of the ladder's journey through the corner, because as you can see here, the ladder is making contact with the innermost corner and the outermost walls. And let's turn our attention to these two triangles here. Notice that these two angles are the same, since these two line segments are parallel to each other and the ladder itself is a straight line. This is the longest ladder that can fit through the corner. If this ladder were any longer, then the ladder would break in half at the innermost corner, and these two angles here would be different. Make sense? Okay, now let's call this distance here x and this side y. Since these two angles are the same, we have theta equals theta, which is tangent theta equals tangent theta, which is b over x equals y over a. And we solve for y and we get y equals a times b over x. So we put this equation aside for the moment, and now we try to find an expression for the total length of the ladder, which is L equals L1 plus L2. L1 is the hypotenuse of the first triangle, and L2 is the hypotenuse of the second triangle. And we have L equals L1 plus L2, which is square root of x squared plus b squared plus square root of a squared plus y squared. And we substitute the first equation into the second equation, and we get L equals square root of x squared plus b squared plus the square root of a squared plus a squared times b squared over x squared. So after a few algebraic operations, we simplify this equation to 1 plus a over x times square root of x squared plus b squared. So now we have a function of the ladder's length in terms of this distance here, x. So how do we maximize this function? You guessed it, my friends. Take the derivative of this function and we equate it to 0, as we always do in problems like these. So the derivative of this is, after we use the chain rule and the product rule, and after all the algebraic manipulations, we end up with this expression here as a derivative. And we equate this to 0. And after we do some algebraic operations again, we end up with x equals the cubic root of a times b squared. And we plug this value into our initial equation. And again, after some algebraic manipulations and simplifications, we end up with L, the length of the longest ladder that can slip through this corner, is b to the power of 2/3 plus a to the power of 2/3 to the power of 3/2. And that's our answer. That's a pretty symmetrical and intuitive answer, if you ask me. Pretty beautiful one, my friends. We'll forego the second derivative test because A, it's pretty tedious, and B, it makes little sense that this is the minimum length of the ladder that can go through this corner. I mean, the minimum length is 0, of course. Wow, what a problem this was, my friends. There are other ways to solve this problem, of course. One involving trigonometric equations, another one involving making use of an XY coordinate system. But this is, I think this is by far the simplest way to solve this problem, in my opinion. I tried to solve this problem in my own way, but I failed miserably. So I think this solution is by far the simplest. Now, this problem is no joke, my friends, and is very interesting. That's why I made this video. Oh yes. I hope you liked it. And there are ways to beef up this problem. You can turn the ladder into a couch, for example. Give the ladder dimensions. But there are no analytical solutions to that problem from what I've read. It turns into a 6-degree polynomial. And as we all know, there are no analytical solutions to a 6-degree equation. There are no solutions to the 5th-degree equation and above, as most of us already know. Also, you can have the two corridors not form a 90-degree angle. It can be some random angle, theta. I'll give that variation a go some other time. I don't know if there are analytical solutions to that. If there is, it's probably going to be ferociously complicated, my friends. So yeah, that's pretty much it. If you have any puzzle suggestions, then send them my way. I'm more than happy to make a video about it. That's pretty much it, and I'll see you guys in the next video. Bye-bye.